those under a 100-year flood that would be sustained for a number of days are shown to be even at a failure condition. Now, the 100-year flood has a 100-year return interval, and the levees have been around for about 40 years, so just because when I say it's a failure condition, that doesn't mean that it has to have been something that's occurred already, because we're talking a 100-year flood. It's kind of a return interval that's longer than what our existing history of the levees is. So the required criteria for the levees to meet includes a margin of safety. So not always where it doesn't meet the FEMA standard is it unsafe or unstable. To kind of restate that, there are a few areas, as I mentioned, these low areas, ponding areas, where it looks to be at a failure condition, but there are also other areas where it's maybe not so low that it's not a failure condition under the 100-year flood, but it doesn't have the margin of safety that FEMA's standards would require. So in a way, the test you're looking at of okay or not okay, those would still be considered not okay. And so therefore, corrective measures are needed in many areas to improve the seepage conditions for the levees and to meet FEMA standards. Now, with seepage under levees, there are a few different design approaches or mitigating approaches you can take to counteract those. And maybe I'll illustrate them here. If the sand layers are not extremely deep and there's kind of impermeable bedrock, say maybe 20-30 feet below the bottom of the levee, or you get into clay layers that are continuous and impermeable, you could maybe construct a kind of a clay cutoff trench that you'd construct under the levee, and that would prevent seepage from moving laterally under the levees. But here, given the depth of the sands, that's kind of cost prohibitive and would also be extremely difficult to construct. So that option does not work. You can also install deep relief wells that would be on the land side and extend deep into the sand foundation, kind of give that uplift pressure a place to go, and the wells would then provide a means of relieving the seepage pressure. Going back to the teeter-totter or balance analogy, you could add a stabilizing berm of soil on the land side. Unfortunately, in Rushford, there's typically not enough space on the land side to accomplish that. The areas where there is open space adjacent to the levees, they're ponding areas, and that ponding area is required to handle internal drainage during precipitation events that would occur at flooding time. But as is illustrated here, because the clay layer is not extremely thick, it is possible to excavate a small trench through there to provide a way for the water pressure that's built up here below the clay layer and doesn't have anywhere to go, to let it kind of relieve itself and seep upwards. That the construction of that trench would, you dig through the clay layer, but then backfill it with a certain type of sand that's designed to filter the water and prevent any material from washing upwards through it. And it kind of would seep upwards in a controlled manner, and then that little bit of water that makes it to the surface would be collected in with any rainfall that might happen during the flood level, during the flood. So this is the kind of illustrating the goal of the drainage trench is that you allow water to reach the surface in a small area near the levee toe. It reduces the uplift pressure, and you don't have a catastrophic failure, what's termed sand boils, that can occur, where water will essentially just start seeping upwards, and it could almost kind of look like a quicksand type situation where the water is just flowing, you know, not seeping, but flowing. You can visibly see it flowing upwards through the soil, coming to the ground surface, and the danger there is that it starts to erode away, carry away soil particles that make up the levee. And if the levee eventually washes away, then you have no protection. You have a breach through the levee, and the flood waters can then flow. So the drainage trench that we're proposing is a way to reduce that uplift pressure that results from seepage through these permeable sand foundation soils for the 100-year flood level. I should say, you know, this isn't the case everywhere, but in many areas, this clay blanket layer just kind of has the right or the wrong thickness, where it creates this this problem where it kind of dams up the uplift pressure, and it needs to be relieved to provide a stable condition under the 100-year flood level. Now we kind of gave this talk here previously, and I understand there may have been some confusion on exactly what the drainage trench ends up looking like. I mean, a trench doesn't sound very appealing. It's dug out to be a trench, and it'll have a certain minimum width, typically 5 to 10 feet, a depth of like 4 to 9 feet, about somewhere in that range. But after it's dug down through the clay layers, it'll be backfilled with a clean sand material to act as a filter, and then even geofabric can be used to separate that from a topsoil, several inches of topsoil material at the ground surface that could be planted with vegetation. So ideally, after X number of months, you wouldn't even see that it's there. So, kind of to summarize our study findings, the corrective measures that we found, or that we recommend to mitigate the seepage issue that we found, include seepage trench. A few low areas, just due to their geometry or whatever, it makes sense to fill them, increase the weight of soil to counterbalance the uplift pressure, but that's not possible, or not feasible in most areas. But there are some areas, and I will show which areas shortly. So this seepage trench or seepage filter varies from about 5 to 10 feet wide, about 4 to 9 feet deep. Be backfilled with sand, a few places also a layer of gravel at the top where we expect a little more water flow seepage into it. And those materials will be specifically selected to work as a filter and keep other material from below from being washed upwards. So that would have the effect of relieving the pressure, allowing water to kind of seep upwards without causing uplift and damage to the levee toe. And the levee toe is kind of like, in a way you could think of it as like the keystone to the levee, where once the toe is damaged, then it kind of can progressively affect the rest of the levee negatively.